Sorry guys, give me a moment. I think there is a problem in the recording. Let me just fix that first. I don't know why this is taking so long. Finally. I was opening the wrong. So I think it will work. Alright, guys. Looks like something went wrong in the recording, so I'm going to record this. Go through this again. This blowing of wind from one place to another has to wait for some time. Hmm. I mean, let's start from the first. So we started from diffusion. Last we started from what is diffusion, and we went through the fixed first law of diffusion and the second law of diffusion. And what has happened is that um, first of all, I would like to apologize to you guys for not the video not working. I don't know why it is doing that. I have absolutely no idea. It suddenly stopped, so I guess I have to just explain it to you guys again, so just bear with me. So the diffusive, what we saw in the last class was fixed first law and the second law. The first law being um, yeah. So what we saw last class was fixed first law of diffusion, where j equal to d into d phi by d dx, or dc by dx. And the second law, we saw the equation which we will be deriving it soon. And we also saw some problem solving approaches, and I would the problems that we are going to discuss are pretty simple. If you have seen all the previous slides and have done your in your work in in terms of the NPTEL lectures. So let me first try to let you make you understand that the fixed first law and second law are interrelated, and that's what we are going to see today. Last class we went through the basics of fixed law of diffusion. This class is just going to be another incremental addition to your knowledge of diffusion, so that you can appreciate it better. So assume that we cut off a small element of a small volume element uh, uh, from the from a solution that is containing a concentration gradient, and the area of the volume element is A, and the width of the volume element is dx, that is which is we are taking an infinite similarly small slice of the solution, so that we can compute what we need to compute. That's what this represents. And now coming to this part of the graph, what we are saying is the diffusivity or the diffusion flux at not all diffusivity is d, so the diffusion flux j at a point x is j of x, and the diffusivity flux at a point jx plus dx is j of x plus dx, and this is the width of the volume element. We are just taking the same volume element, and we are just giving the names of the various factors that are involved. Now what we are going to do right now is that we are going to define local concentration gradients, or local concentration and diffusion flux at a point x and at a time t, which is c of x at t and j of x. Now we have these two equations. Let's look at this equation first. j of x plus dx, or we are talking about the flux at x of dx, is equal to j of x plus dj, which means that the flux at the diffusion flux at x plus dx is equal to the diffusion flux at the point x plus dx is equal to the diffusion flux at the point x plus whatever changes that may have occurred in the diffusion flux within this volume element dx. That's what this equation implies. Now let's look at this equation. um, so I'm this equation is part of a problem that we are going to solve, so I'm not going to give you the whole meaning of this equation. I'm going to give it to you at the end. But let me give you an intuitive understanding of it. So the DC, or the whatever difference we find in the concentration of the molecule which is diffusing down a concentration gradient at a point x, that's what C of x of t means, right? So C of x of t means that the concentration of the solute at a point t, at a point x at a time t, and the change when it goes from x to x plus dx is the change in the concentration between the point x and between the point x plus dx is denoted by dc. So intuitively, you should understand that that is related upon the flux of diffusion, J of x at the point x, and J of d of x at the point x plus dx. Sorry, J of x plus let me repeat that sentence again. Um, Intuitively, this change in concentration dc, you should know that it should be related to the flux at a point x, which is j of x, and at a point x plus dx, which is j of x plus dx. So they have given it here as that. So uh, this the difference in the concentration between this point and this point is basically the difference in the flux. It's related to the difference in the flux at this point and this point, which is given by this equation. That's what it says. I'm going to make you think about how this equation came in the first place. We'll look at it later. Now let's try to now let's go to the problems. The first problem is how we arrive at this term, which I said that I'll explain to you later. And how to derive Fick's second law from the data from the previous slide. You know, these two equations are enough to derive the Fick's second law. And the third question is how to arrive at the Fick's first law from the second law. Right now, I'm going to wait for another 10 or 15 minutes for you to just absorb what we have just said. To reiterate, give you a glance again, what we did was we took a volume element from a solution which was whose width was infinite semial, which is dx, and whose area is a, and the diffusion fluxes at the point x and the point x in dx are defined by j of x and j of x plus dx respectively, and the volume element here is just or the width of the volume element is dx, and we have arrived at these two equations. Now assume that this equation is right, now what we need to do, we are addressing problem second, how to derive the Fick's second law from these two equations. How would you go about it? Like like in the last lecture I said, we the under the you don't need to understand much in this question, right? It's very straightforward. For derive Fick's second law from these two, so look at the data carefully and think about how you will uh, you know uh, um get the uh, get to Fick's second law using these two data. I'll give you 10 or 15 minutes time. So any idea, guys, how to go about this? So basically, we know that j of j plus x plus dx equal to j of x plus j of dj. We have to substitute it here, and once we substitute and rearrange, this dt goes to here. So that is how the equation transforms to this. For people who would want to see how those two data points or those two equations translate into this equation, I would suggest you take a paper and a pen, and you just substitute this equation into this equation and find it out yourselves. So we still have problem one, that is the suspense that we will discuss at the end. So once you do this, you must remember from the first law where J is equal to the diffusive flux equal to the negative of d into dc of x by dx. That is the first law of fixed first law. And why the negative sign? I was asking the question in my previous week. I hope you people were able to understand it. So uh, coming to the fixed first law, uh, what we know that j is equal to this, so we are going to substitute this here. So basically it will become the negative of d by dx of the negative of d into dc by dx at a point x. Both the negatives cancel, which becomes d into d by dx of dc by dx, which is the second derivative of the concentration at the point x. So that is how we arrive at fixed second law. Again, for people who have difficulty in understanding this, how we arrive at fixed law from this, I suggest you substitute 1 and 2 and find it out yourself using a pen and paper. Now let's go to problem 3. How to arrive at fixed first law from the second law. We know that the fixed first law is given here. It's given here also. It was given here, but I did not want to just put it here so that you might try it yourselves. But fixed second law is given explicitly in the second lecture, which is the rate of change of concentration with respect to time, dc by dt equal to d into the second derivative of dc by dx square. Here c is replaced by phi. You can replace it with anything you want. How you want to call it, it's your call. And so the question is how to arrive at this fixed first law using the fixed second law. That's the question. How would you go about it? During the time you think about it, let me go see how many people have actually viewed the videos. So all you have to do to access the videos is just go to YouTube. The link is public. Anyone who wants to listen to it can listen to it. And then type transport phenomena in biological system. Yeah, transport phenomena in biological system channel. All right. Yeah. Week 2. Looks like nobody has seen the week 2 video. If you have not seen the second the video of week 2, you will not be able to make head or tail out of what I'm talking right now. So I suggest you go and look at uh, these videos. Yeah, transport phenomenon. Yeah. Oh, actually, I was wrong. Mm. So week 2 video was viewed by 1. Week 1 video was viewed by 3 people. Totally unimpressive when compared to the strength of the transport phenomena and biological systems course. I mean, I get it. I understand that all the people here are can make do on their own. They understand the basics of calculus pretty well, I guess. Alright, let's go to question 3. How do we arrive at fixed first law from the second? It's simple, right? So basically, what is fixed? Um, Let me give you a clue and then wait for a minute or two. So Fick's law assumes equilibrium, or in other words, it assumes that the rate of change of concentration with respect to time at a position x is equal to 0. Now, now let's see how many people has gotten it. Still only me, yeah? So dc by dt equal to 0. So dj by dx equal to 0. So how would you come to fix first law from dj by dx equal to 0? That's the question. So meanwhile, in the last class I gave you a question in that blowing of wind from one place to another is considered diffusion, but can be considered as diffusion. But I asked an even more specific question where I made a statement where both wind power and solar power are the same. I assume that there was only one view, right? So nobody looked at it. So what could be the reason for wind energy to be the same as solar energy? Um, so basically, the sun heats up the Earth's surface in an uneven manner, and as it heats up at the surface in an uneven manner, some parts of the our planet, the molecular the collision of the molecules that make up our not the atmosphere, the makeup inside our atmosphere. Then 78 parts of nitrogen, 22 parts of oxygen, and etc. 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 When you heat up this air differentially from at one place and with respect to other, in other words, when the temperature of one place in Earth is higher than that of the other, it creates a lot of collisions between the molecules, which which in turn, I don't want to go into the details, which in turn creates a pressure gradient. So these gradients, right, these concentration gradient, pressure gradients, etc., 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 they are all the same. So in fact, the principles of diffusion are can also be applied to heat convection, conduction. I mean heat conduction, etc., etc. So so because of this differential heating, there's a wind that flows from one place to another. So since wind turbine catch this energy by by harnessing the flow of wind through their turbines, as the wind moves from one point to another and generate electricity. So wind energy is indirectly another form of solar energy. In fact, everything that you see around you, including yourself, is a form of solar energy in this planet. That is. So I hope you were able to deduce this. We left it at dj by dt equal to 0, and we said that we'll arrive at fixed for second law. Sorry, first law from that. It's very simple. You do the reverse of what you did when you arrived at this fixed second law. So dj by dx equal to 0, or d by dx of j, which is you know one second. Yeah, this is the lecture that I used to create these slides. You can go through this lecture. So it's yeah, yeah. So basically, it's actually the reverse of reverse of what we did to arrive at fixed second law. dj by dx, we know that j is equal to minus d by dx of dc by dx at a point x. So dj, if you substitute for j here, and this becomes 0, and if you know rearrange everything, um, this becomes the fixed first law. So that's how you go about it. And now coming to the first question, how did we arrive at the term dc by x? This term. I'll give you an example. I'll give you a clue where you need to look at the units of j, which is number of molecules, which is the j is diffusive flux, or the transport of the number of molecules per unit area per unit time. So how is this equation formulated? Did they do any magic to arrive at this equation, or this equation can be deduced graphically from here? We know graphically from here. We know that the change in concentration dc is related to the change in the diffusive flux at the point x, which is given by j of x, and that of point x plus dx, which is given by j of x plus dx, right? So let's see how instead of mechanically arriving at equations from big derivations and stuff like that, how the author has simply used this graph to arrive at this part of the equation. So you just need to look at this graph more closely to arrive at this. It's as simple as that, and you need to look at the units of j to validate your assumptions. I'll give you some time to think about it. How we arrived at this first law, I think you should, if you don't understand this equation 2, you won't be able to go through, go through either problem 2 or problem 3. So I suggest you look at lecture 2 before trying to understand this, because in lecture 2 I gave you enough intuitive understanding of what this equation means. In fact, we built up the whole presentation based on the first law, and not the whole presentation, a good part of the presentation. So I suggest you go through the uh, lecture slash presentation in week 2 to understand this equation. Now, how will you arrive at this equation? That is the question, and I'm going to give you some time to think about it, and I'm going to give you some time to think about this graph and come up with the answer. And once more, I'm giving you the clue again. Look at this graph. Look at the unit of diffusive flux, which is number of molecules per unit area per unit time, and Those are the two clues you need to work with. Come on, get it done. All right. I think you have had. Chalo, you take 2 more minutes. Just look at the graph. You'll understand the equation, especially the left part of the graph. Chalo, let me explain it to you. Now I already told you that the difference in concentration between this volume element has to do something with the difference in the flux at the point x and the point x plus dx, which is mentioned here, g of x minus g of x plus dx. Now, so basically, that is only for a point in plane, on the left side of the volume element, which is represented by the x, and the right side of the volume element, which is represented by x plus dx. Now, how would you take it for the whole volume element? That is the question. So basically, you multiply it by the area, and that's all. You got it. And multiply it by area and multiply it by the time element also, so since c is a function of x of t. Now just taking this, that is a numerator. I would suggest what you do is now try to if you take the units of flux. So the unit of this is number of molecules per unit per unit area per unit time. The unit for this is time, the unit for this is area. So basically area inverse and time inverse in this um, in this in this term gets cancelled, and we get the number of molecules, difference in the number of molecules in this between these 2 points. Now what we need to know, what is the final thing that we need to do. So we took a slice of solution, slice of a solution with a volume element with a width dx, right? So basically, we have at this point of time, we have looked at the area, only the area of the diffusion at a point x and the diffusion at a point x plus dx, and we have taken into consideration the area. Now, concentration is a function of not area but volume. So area is given by meter square or centimeter square, whereas volume is given by centimeter cube or meter cube. So you have to divide it by the whole volume element to get the concentration. So this is the number of molecules, or the difference in the number of molecules. Now, how to represent this difference in number of molecules in terms of concentration? You need to have uh, a volume element in the denominator. So how to get the volume element in terms of this graph? So basically, the area of this volume element is A, and the width of the volume element is dx. So basically, the volume of this volume element or the slice of solution is A into dx. So that's what is in the denominator. So basically, the number of molecules in the numerator, and looking at it, for the area's unit is centimeter square, and the unit for x is also distance, centimeter. So it becomes centimeter cube. So it becomes the number of molecules divided by centimeter cube, which is the concentration. So you see how simple this has been. Instead of racking our brains with in terms of mathematical you know I guess you would have been solving a lot of differential equations in your assignments, which is also required. That rigor is also required, but the foundation for all those things have been the graphical interpretation. Not all those things, a foundation, or let me put it this way, a better way, a very easier way to understand everything in calculus is to understand it in a graph, from the point of view of a graph. If you are able to first read a question, or think about a system, whichever way you want to look at it. If you want to understand the rate kinetics, or the rate of change of certain things in that system, I suggest you look at it in terms of a graph, or you inside your mind. If you're able to draw the graph, it's perfectly fine. But if you're not able to do that, take a piece of pen and paper and draw a graph like this. You'll easily deduce what you need to understand. So from this graphical interpretation, we have come to this. So I'll repeat again. So this I'm not going to repeat. J of x minus j of dx. So j of x minus j of dx represents the at a point uh, per unit area per unit time. So basically, since c is also a function of time, we need to take the the time element dt, and we need to multiply it by the area. Since the unit of this is number of molecules per unit area per unit time, we need to multiply it by the time element dt and the area. Now, once you do that, once you simplify it, it will become number of molecules per unit area per unit time, or number of molecules per unit area per unit time into the time element for which the unit is time, and the area element which is which whose unit is centimeter square. So basically, the denominator units gets cancelled, and at the numerator we get the number of molecules, or the difference in the number of molecules. Now we need to put it in a way in terms of the difference in concentration. So concentration is just or the difference in the concentration is just the difference in the number of molecules per per unit volume. That's how concentration is defined. And what is the volume here? We took a uh, slice of a solution whose area is a and width is dx. So basically, a dx is its volume, and a dx unit a is unit is centimeter square, and x unit is distance, which is also centimeters. So basically, we get centimeter cube. So number of molecules per centimeter cube, or dc. So we bring dt here this side. So dc by dt. No, before going to that, we just let's first understand what dc is. dc is a change in the number of molecules per unit volume. Yeah, that's how we arrive at this equation from this graph. Simple, very simple. And after that, you just bring dt this side, do the substitutions. I think we talked about it. I'm not going to repeat it again. And yeah, again I reiterate, if you have any issues in terms of thinking about a system and understanding its state kinetics, please look at it graphically. uh, if you're able to, I would suggest that, because that's the easier approach. And yeah, that's about that. I think we have come to the end of this end of the presentation. And let me just go through the second presentation. I've asked one question here. So if the concentration, if you have looked at video 2, if the concentration these represent concentration gradient as explained in week 2 video. If the concentration gradient is higher or lower, will the diffusivity of a molecule will change? What is the likely impact on diffusivity? The answer is 0. Diffusivity is the intrinsic property of a molecule. It has no bearing on the concentration gradient, and the higher the concentration gradient, the higher is the diffusional flux, but there is no change in the diffusivity. That means if you take two different solute molecules with different diffusivities with the same concentration gradient, you cannot expect the diffusional flux to be the same for both of them, for the simple fact that the diffusivity of these two different solute might be different. Let me put that in a very simpler way. Let's take two solutes whose diffusivity is different, d1 and d2. Now you create the same concentration gradient. Now you cannot expect, given a time interval, the concentration gradient would have changed identically for both the systems. That is because both the systems has the solute particles in both the systems are different diffusivity, and diffusivity is what determines the actual. It is one of the determining factors of the actual diffusion kinetics of the of a given solute, and diffusivity is a function of the mean free path, and etc etc. I'm not going to go into that. That's beyond the scope of the discussion. But people who are interested see how diffusivity is defined in terms of from a molecular basis. If you look at that equation, you will clearly understand what I'm trying to tell you. So it's very important for you to understand that there is no, for a given solute there will be no impact on diffusivity, and different solutes will have different diffusivity, and that will determine that's a very important determinant in how a ligand binds to a protein, how a receptor brings in water molecules inside the cell, how a receptor brings nutrients into the cell. We talked about it last time in terms of active and passive diffusion. So that's very important. And yeah, so that's about that. I think we are done for today. I think today was a bit more of data. It's not more data. In fact, the number of slides is very less, 6 slides. But the concept that I explained to you from the graph might have gone over the head. I don't know. I cannot presume that. But if it has gone over your head, I suggest you to relook at this. Have a relook at this presentation, relook at this video along with the presentation, and please try to understand this equation in terms of this graph. For people who want to be scientists in the future, calculus will be, um, in all fields, even perhaps some cases in economics also, all types of scientists would require some basic understanding of calculus. And if you are able to arrive at equations from graphs, nothing like that, you understand calculus intuitively. You don't need to understand the mathematical proofs. You don't need to understand the limit extends to zero, all those things, and then how they arrive at the specific formulas for specific uh, equations. That and all you don't need to understand. If you are able to understand this graph and understand this equation, and if you are able to think of a system and think of it graphically and write your own differential equations, then you have understood calculus in my view. So with that, we would stop for the day. Again, I thank you for well, there are no people here to thank, but I'm thankful for you for NPTEL to have given me this opportunity to discuss about these things, and I hope people will look at these videos sometime in the future. And thank you. Bye bye.